Dear viewers, today we are going to start a new topic, that is silicons and phosphazenes. In this lecture we will be studying silicons. So, before starting silicons, let me introduce the element silicon. Element silicon is an element with atomic number 14. It is the second member of group 14 elements. It resembles carbon and boron in its properties. It resembles carbon because it lies in the same group. It has a valency of 4 like carbon, and it resembles boron because of the diagonal relationship of this element with boron. So, to start, let us also understand the term polymers, because we will be studying silicon polymers, different type of silicon polymers in this lecture. A polymer is a large molecule which is composed of many repeated subunits called monomer. That means monomer and polymer, they are monomer is a basic unit, mono means one and poly means many. Many basic units, that is many monomers, they join together to form a large molecule which is called polymer. Polymer touch and influence almost every aspect of modern life, from electronic materials to medicines, from fibers to structural materials, from familiar synthetic plastics such as polystyrene to natural biopolymers like DNA and proteins. A polymer can be both natural and synthetic, and these are created through polymerization of monomers, that is the monomer units, they get polymerized to form the polymer. Their consequently large molecular mass produces their unique physical properties like their toughness, their viscoelasticity, viscosity, and their tendency to form glasses and semi-crystalline structures rather than crystals. So, before going to the lecture, let us see the lecture plan. So, in my lecture I will be discussing the introduction of silicons. We will compare the organic and inorganic polymers, then the properties of inorganic polymers, the glass transition temperature, nomenclature and preparation of silicons, the factors which affect the nature of silicon polymers. The polymer can be both organic or inorganic. The inorganic polymer are basically formed by the atoms of group 13, 14, 15 and 16. Group 13 include the boron family, group 14 is the carbon family, group 15 is the nitrogen family, and group 16 is the oxygen family. These form the core of the inorganic polymer, while organic polymer have a backbone which is made of carbon and which are linked together by nitrogen or oxygen. With different valencies of inorganic elements, different group can attach to the atom of the polymer, while this is not the case with the organic polymer, because here the central atom is carbon, which shows only one valency, and that is 4. The presence of different group in the inorganic polymer alter the properties of the polymer, their stability at high temperature and their solubility in different solvents, but this is not the case with organic polymer. These are not very stable at both high and, but with organic polymer this is not the case, because these are not very stable at both high and low temperatures. The bond present in inorganic polymer are longer and stronger, and they resist free radical cleavage, but the bond present in organic polymer are not very strong. Coming on to the introduction of silicons. By analogy with ketones, the name silicon was given in 1901 by Kipping to describe new compounds with the formula R2SiO, where R is the alkyl group, Si silicon and oxygen. These were rapidly identified as being polymeric and actually corresponding to polydialkyl siloxanes. Silicons are polymers that are made up of repeating units of siloxane. That means siloxane is the monomer which keeps on repeating itself to form the polymers. The functional group siloxane is basically made of 2 silicon atom and 1 oxygen atom combined together with the oxygen, and their valencies is fulfilled by carbon and hydrogen. They are typically heat resistant and rubber like and find surplus use in modern life as sealants, adhesives, lubricants, medicine, cooking utensils and thermal and electrical insulations. That means these shows many applications in the modern life. Some common forms include silicon oil, silicon grease, silicon rubber, silicon resin, etc., and all these we will be discussing in our lectures. Properties of inorganic polymers. The inorganic polymers do not burn except a few exceptions, but they soften on heating. At very high temperature, they tend to burn. Most of the inorganic polymers are polar in nature. That means these develop a positive and a negative charge, and they therefore react with the solvent instead of dissolving in them. These are stiffer and harder than the organic polymer due to their cross-linked structure and the presence of large number of covalent bonds. So, the large number of covalent bonds which are present in the inorganic polymer make their structure very hard. The polymers have cross-linked structure and do not permit the interaction of solvent molecules because of short chain segment between the crosslinks. Crosslinks are present in these polymers which do not allow the solvent molecule to enter into them, therefore, they do not interact with the solvent. These are less ductile. Ductility is basically a property by which a metal or any element it tends to stretch like a wire. So, these inorganic polymers are not very ductile, these are less ductile than organic polymers. Therefore, they break even when stretched to 10%, while organic polymer like polyethylene it can extend up to 20%. These are stronger, harder and more brittle than the organic polymer. Brittlity is a property that means cracking. If it drops, the polymer cracks. These can be obtained in pure crystalline and pure amorphous form, but organic polymers have partial crystalline and partial amorphous form. Coming on to the glass transition temperature, which is denoted by Tg. The glass transition temperature is the temperature at which the internal energy of the polymer molecule increases to such an extent that the chain segment of the polymer molecule leave their lattice position. That means, if we keep on increasing the temperature of the polymer, then at a certain temperature which is the Tg, that is the glass transition temperature, then the chain segments present in the polymer they leave their lattice position. And at this temperature the chain segments start moving apart from one another even on applying a very small strain to the polymer. Because the chain segment they have left their position, so if a very small pressure or strain is applied to the polymer, the chain segment they start moving apart. The glass transition temperature depends upon the chain length, that is how long is the chain, whether it is a short chain or a long chain. It depends on degree of cross linking, that means whether it is a linear polymer or a cross linked polymer, and if it is a cross linked polymer, that what is the degree of cross linking in the polymer. It also depends on the barrier restricting the internal rotation around the chain links. That means if we have a polymer, then it is not easy to rotate the polymer. There is some barrier which stops its rotation. So, it depends on that barrier. Below this temperature, the chain segment of the polymer are fixed on their lattice sides. The polymer in this condition is hard, brittle and breakable like glass. Means if the Tg has not been reached, that means the glass transition temperature has not been reached. At a temperature below this temperature, the polymer would be hard, brittle, that means it will easily break like a glass. At this temperature, the segment of the polymer starts to diffuse like the molecule of the liquid. Because the chain segments they have left their lattice positions, so now they start moving and they start to diffuse. And at a temperature higher than the glass transition temperature, the polymer is present in the molten form, because the chain segment they have left their position and now they are free to move like a liquid. We can see in this figure, here we can see that a bond between PO it starts to break, and new bond between this phosphorus and this oxygen they starts to form. Here also we can see one more bond is being formed between P and O. So, as the temperature is increased, some bonds they break and some new bonds are formed, and in molten state we can see that this chain segment has broken and new segments they are formed, and now they can easily move because these leave their lattice position, they can easily move and diffuse with each other. The cross linked inorganic polymer show a wide range in their glass transition temperature. In this temperature they change from rigid solid to leathery solid. That means, if we talk about the cross linked inorganic polymer, initially they are present in the form of rigid solids, but if the temperature is raised a bit, then they change to leathery solid, means solid in the form of leather, which is somewhat flexible. If the temperature is further raised, they change to rubbery solids and finally to viscous solids. But if we talk about the linear polymer, so the glass transition temperature of a linear polymer is very sharp, because the movement of the chain segment from one side to another does not involve the exchange of bond, as happens in the case of cross-linked inorganic polymers. So, here the polymer would be present in a solid form and finally it will change to the molten form. There would be no such transition like it will go to leathery form or rubbery form. So, it will be a straight conversion from solid to liquid. Silicons. Silicons are the compounds that are polymeric organosilicon derivatives containing silicon oxygen silicon linkage. These are also called polysiloxanes and are represented by the general formula R2SiO(N). N is the number of monomer unit. So, this is the structure of a silicon polymer. Here we can say silicon, it has a valency of 4, 2 valencies are occupied by alkyl group, this can be aryl also, and one is occupied by oxygen. On the other side we can see this bond, these two bonds which cut these bracket, these shows that the molecule has not finished, this is just a monomer unit, the molecule extends up to n number of units, that is a polymer. These may be linear, cyclic or cross-linked. These are also called high temperature polymers because these have very high thermal stability because of this silicon oxygen silicon bond. Therefore, these find use in high temperature applications like heat transfer agents and high performance elastomers. Organic polymers, on the other hand, do not find such uses because they cannot withstand high temperatures like the silicon polymers. Coming on to the nomenclature of silicons. These also follow IUPAC nomenclature. IUPAC is International Union of Pure and Applied Chemistry. The basic unit here is SiH4 and it is named silane, like in the case of organic compound we find that the basic unit is CH4, the methane, it is called methane. The second unit is ethane, then we have propane, butane, pentane and so on. Similarly, we have silane if it contains one unit. If there are two units, it is called disilane. Silane correspond to methane, disilane correspond to ethane. If we have 3 units, it is called trisilane and it correspond to the propane. Similarly, we have tetrasilane, pentasilane, hexasilane and so on. Coming on to the nomenclature of silicons. Here IUPAC system is followed. IUPAC is the International Union of Pure and Applied Chemistry. Here the basic unit is SiH4 which is called silane, like in case of organic compound we have methane CH4. So, silane correspond to methane in organic chemistry. The second unit, that is which consists of 2 silicon atom, is called disilane, it corresponds to the ethane as we have in organic chemistry, which is C2H6. If it has 3 silicons, it is called trisilane, it corresponds to the propane. Similarly, we have tetrasilane, pentasilane, hexasilane so on depending upon the number of silicon atoms. If the aryl, alkyl or halo substituted silane are present, then they are named by prefixing the silane by the specific group, like we have Cl2 SiH2, here 2 chlorine are present. So, it is named dichlorosilane, the chlorine is used in the prefix. In this case, we have 2 chlorine and 2 methyl. So, the name will be dichloro-dimethylsilane. The name could have been dimethyl dichloro, but we use chloro part first because if there are 2 different substituents, then we follow the alphabetical order and alphabetically C comes before M. Therefore, the name would be dichloro-dimethylsilane. Here we have 3 chloro part and 1 methyl group. So, the name will be again chlorine will be named first. So, the name would be trichloromethylsilane. Silanes containing hydroxy groups are named by adding the suffix. The suffix used for hydroxy group is -ol. If there are 2 hydroxy group, it would be named diol. Similarly, for 3 it would be triol depending upon the number of hydroxy group. For example, we have SiH3OH. In this case, we have 1 silicon and 1 OH. So, the name would be silanol. If OH would have not been there, then the name would be silane. So, now 1 H is being replaced by 1 OH. So, in silane the spelling is SILANE. The E would be replaced by all, the name would be silanol. In this case we have 2 OH. So, the name would be silane diol. So, in place of E, the last E which was used in silane, it would be replaced by diol. Here we have 3 OH group. So, the name would be silane triol. In this case we have methyl and OH, both the parts are there, and we know the methyl substituents or alkyl substituents, they are used in the prefix, while the hydroxy substituents are used in the suffix. So, the name would be tri, because 3 methyl are present, trimethyl silanol. Oxy derivatives are named as siloxanes. For example, we have this particular example SiH3 OSiH3. So, these SiH3 units are joined together by oxygen, the name would be disiloxane. Here we have, this is also disiloxane, but here the hydrogen has been substituted by the methyl group. So, 6 methyl group are present here, the name would be hexamethyl disiloxane. Polymers are named by specifying the side groups and then the backbone. For instance, we have this particular example, this is a polymer which is indicated by these 2 bonds. So, the name would be, first of all we will use the word poly for the polymer, then we have dimethyl siloxane, this unit is dimethyl siloxane. So, the name would be polydimethyl siloxane. In this case we have, this is also a polymer and we have ethyl and phenyl group. So, the name would be poly for the polymer, and methyl and phenyl, methyl the M of methyl comes prior to the phenyl P, alphabetical order is followed here. So, the name would be polymethyl phenyl siloxane. In the first method, the substituted silicon halide, that is R2SiCl, are prepared. Silicon is converted directly to tetrachlorosilanes. So, here silicon is treated with the chlorine to form tetrachlorosilane SiCl4. This tetrachlorosilane is then treated with the Grignard reagent, that is RMgX. So, this is tetrachlorosilane, it is treated with RMgX, and R2SiCl2, that is substituted silicon halide are formed. A variety of chlorosilanes are produced by this method. Second method is the Muller-Rokow process. This is a direct process in which alkyl chloride is treated with elemental silicon at 280 to 300 degrees Celsius and a high pressure of 200 to 400 kilopascal in the presence of a catalyst, which is copper. In this reaction, RSiCl3 and R3SiCl, that is trichloroalkylsilane and chloro-trialkylsilane are produced, which are the side products and are removed by distillation. Compounds with the formula R2SiCl2, that is dichlorodialkylsilane, are of the utmost importance because they provide the starting material for the preparation of a wide variety of substances having both organic and inorganic character. Nature of the product formed during this reaction, it depends upon the temperature, the pressure and the catalyst used. It also depends on the silicon purity. Basic catalyst and high temperature yields higher molecular weight polymers that are linear. That means, if we use a catalyst which is base and a high temperature is used, then they will give high molecular weight linear polymers, while acidic catalyst if used, they will give low molecular weight cyclic polymers. Third method is hydrolysis of R2SiCl2. In this method, the chloro group is replaced by hydroxy group simply by the hydrolysis. Here we can see we have dichloro-dimethylsilane. It on hydrolysis, the 2 Cl group, that is the chloro group, they are replaced by 2 hydroxy group and we obtain dimethyl silane diol. After this dimethyl silane diol is obtained, the polymerization takes place through the elimination of a molecule of water from 2 hydroxyl group of the adjacent dimethyl silane diol. Next is the formation of linear silicons. In linear silicons, we can see we have different silicon units, like one is present here, the other is here, and between these two silicon units we find these have OH. A water molecule is eliminated from the two, OH from one and the hydrogen from the other, and these two units they now joined by the oxygen. Similarly, the OH group of this and the OH group of another unit they react and water is eliminated, and again these two gets joined together by the oxygen atom, and similarly this type of process take place and a linear silicon is formed in which the different silicon atoms they are joined together by the oxygen. Formation of cross-linked silicons. Aryl or aryl trichlorosilane gives cross-linked silicons on hydrolysis. These are obtained as a fraction of preparation in dichlorosilanes or can be prepared by the following methods. So, in this by this method we have prepared the alkyl silane, and in this method we have prepared the aryl silane. In alkyl silane we have treated chloromethyl with silicon and HCl in presence of copper and high temperature, while for obtaining the aryl silane we have treated the trichlorosilane with RMGX, that is the Grignard reagent. Here the R part is the aryl part, it is phenyl magnesium chloride, and we have obtained trichlorophenylsilane. The hydrolysis of alkyl trichlorosilane takes place as shown here. Here we have seen we have trichloroallyl silane. This can be the allyl or aryl part, any part as we have seen earlier. It on hydrolysis, that is reaction with water, it gives this allyl silane triol. Here we have seen that 3 chlorine part they are replaced by the 3 OH parts. This is followed by the polymerization to give the linear compound. Again here 2 monomer units they join together and a water molecule is eliminated, and these two get joined together by the oxygen. Similarly, the second unit it joins to the third unit, again a water molecule is eliminated and these two get joined by the oxygen, and this type of linear polymer is obtained. Now, this linear polymer, presence of the OH group at the end of silicon chain and below and above give rise to polymerization to give a cross link. The linear polymer obtained in the earlier slide, we can see that 2 such units they have joined here, and the silicon joins to the other silicon unit in the second dimension through oxygen atom to form a cross link polymer. This link can extend to any length and any dimensions to form a cross linked polymer. The cross linked polymer can extend in 2 dimensions to any length and in any manner. Silicon polymer of any type, whether straight or cross link or even mixed, can be obtained by mixing the right amount of trialkyl chlorosilane and dialkyl dichlorosilanes and subsequently their hydrolysis takes place. The trimethyl silanol obtained by hydrolysis of trimethyl chlorosilanes contain only one OH group, and hence it can be used to block the chain to get a control chain polymer, because here only one OH is present and this OH it reacts with the OH of other group and water is eliminated, and no further OH is present in this group, therefore, no further polymerization take place. Therefore, these type of groups which contains only one OH are used to control the chain polymer or used to stop the chain polymers. Therefore, R3SiCl is regarded as chain stopping unit, because this Cl when it is hydrolyzed it converts to OH and this has only one OH unit in it. Therefore, it will stop the further chain polymerization. The ratio of R3SiCl and R2SiCl2 in the starting mixture determines the average chain of the polymer. Cyclic polymers with 3, 4, 5 or 6 silicon rings can be prepared. Like in this case, we have trimethyl silanol. 3 units of this are polymerized and they form tris cyclo dimethylsiloxane. This is a 6-membered ring, but here 3 silicon units are present. Therefore, it is a 3 silicon ring compound, and therefore, we use tris word here. Tris is basically used for complex systems. We use tris for 3, bis for 2, tetrakis and pentakis for 4 and 5 and so on. Similarly, here 4 units of trimethylsilanol are used and they get polymerized to form a 4-membered silicon cross-linked system, which is named as tetrakis. Tetrakis is for 4, we have 4 silicon units here. Tetrakis cyclodimethylsiloxane. Phenylchlorosilane can be prepared by reaction of trichlorosilane and benzene in the presence of suitable catalyst such as boron compounds at 300 degrees Celsius and high pressure. Here we have trichlorosilane which reacts with benzene at high temperature and high pressure in presence of boron compound to form trichlorophenylsilane. Now, coming on to the factors affecting the nature of silicon polymers. The various factors which determines the silicon polymer are the length of the chain, whether it is a long chain or a short chain, the distribution of the organic group if there are more than one type of R group. This R group is basically the organic group, whether it is alkyl or aryl, and in alkyl whether it is methyl, ethyl or any other group. It also determines the silicon polymer. The extent of cross linking, how much is the cross linking, whether the linear polymer is there or a cross linked polymer is there, and in cross linked polymer what is the extent of cross linking, whether the cross linking is less or more. It also affects the silicon polymer. The nature of the aryl or alkyl group, as I have already discussed, whether it is a short group or a large group. The type and proportion of the structural units. In general, short chain silicons are oily liquids, medium chain silicons are viscous liquid like greases and viscous oils, while those with very long chains or long cross linking are rubber like, that is a bit hard polymers. So, this was all about the today's lecture. Coming on to the summary. In our lecture, we have discussed the polymers, how they are formed and what are the basic units, that is the monomers present in them. Comparison between the organic and inorganic polymers was also studied. Then we have introduced silicons, their polar nature, they are harder, stiffer and they do not burn at low temperature and they can resist a very high temperature also. We have also studied the properties of inorganic polymers. After that, we have studied the glass transition temperature, that is the temperature at which the internal energy of the polymer molecule increases to such an extent that the chain segment of the polymer molecule leaves their lattice position. At this temperature, the chain segments start moving apart from one another even on applying a very small pressure or strain to the polymer. Silicons was the next topic we studied today. Silicons are the compounds which are polymeric in nature. These are basically polymeric organosilicon derivatives containing silicon oxygen silicon linkages. These are also called polysiloxanes and these are represented by the general formula R2SiO(N), where R is the alkyl group and N is the number of monomer units. We studied the nomenclature of silicons, in which the basic unit is SiH4, which is called silane. Then we studied the preparation of silicons with various methods. The first one was from silicon halide, then we studied the Muller-Rokhoff process, the hydrolysis of R2SiSCl2, formation of linear silicons, formation of cross-linked silicons. We also studied the factors affecting the nature of silicon polymers, which are the length of the chain, the distribution of organic groups, the extent of cross-linking and the nature of the alkyl and aryl group and the type and proportion of the structural units. In the next episode on the same topic, we will be discussing the equilibration and ring opening polymerization, which is also called ROP. Then we will study the properties of siloxanes, their uses, silicon fluids and oils, their preparation and properties, silicon elastomers, that is rubbers, their properties, preparation and uses. Then we will study the silicon resins, their properties and uses. Thank you.